Good afternoon, ma'am. My name is Akila. I am from CSM A section. My topic is gated recurrent unit. Gated recurrent unit is a simplified approach to sequence data pre-processing. GRU means it's a full form of the gated recurrent unit. It is a type of a recurrent neural network RNN. It is introduced by Koyana Cho in 2014, designed to solve the problem like vanishing gradient problem, long-term dependency issues in RNN. What is gated recurrent unit? The gated recurrent unit is a specialized type of a RNN architecture introduced as networks designed to capture and learn from dependencies and the sequential data. GRU offers a streamlined approach with fewer computational requirements. Here are the key characteristics. The first one is the reduced parameter count. Next, faster training times, efficient memory uses, and simplified architecture. Unlike a traditional RNN that struggles with long term dependencies, gated recurrent unit introduces a gating mechanism that allow it to selective remember or forget information over the time. This makes it particularly effective for processing sequence where the order and timing of elements matter significantly. Next, we are discussing about the problems with traditional RNNs. Standard recurrent neural networks face significant challenge when processing long sequence when they are excel at capturing short term dependencies. They struggle with information that spans many time steps. Here, vanishing gradient problem means during the back propagation, gradient becomes exponentially smaller as the propagate backward through time. This makes it difficult for the networking to learn, update, wait for earlier times steps, effectively preventing the model from learning long term dependencies. And the second one, exploding gradient problem. Less commonly, gradient can be become exclusive large training, causing unstable update and preventing the gradient clapping and mitigate this issue. It does not add fundamental problems of information overflow. And next, why gated recurrent unit was developed? The LSTM solution. Here, the long term short term memory network successfully addressed RNN limitations through sophisticated gating mechanisms and separate cell states. However, these came at the cost of increased complexity. However, these came at the cost of increasing complexity, more parameters, and longer training times. And we are introduced for that has a simple and more efficient solution that maintain the ability of the capturing long-term dependencies while reducing the computational overhead by combining elements of LSTM architecture. GRU achieves comparable performance with fewer operations. Here the key insights: GRU can be seen as simplified version of LSTM that trades a small amount of significantly improved efficiency. Next, the hidden state, which means unified memory, a single state design, unlike LSTM, which maintains separate cell state and hidden state. GRU combines both into single hidden state that serves dual purpose. The hidden state in GRU stores both short term and long term information through gating mechanisms. This unified approach that reduces the number of parameters and simplifies the architecture while maintaining the ability to capture the temporal dependencies. At each time step, the hidden state is updated based on the current input and the previous hidden state, with the gates determining how much information to retained discard. The two gates of GRU. Here the first one, update gate, and second one, reset gate. The update gate determines how much past information to keep in the hidden state, acts as a combination of LSTM forgot input gates, controlling the balancing between add and the new information. Reset gate means it determines how much past information to forget or ignore. Model focus on relevant short-term dependencies by filtering historical data. These gates works together to control information flow. The network, both gates used sigma activation functions and between 0 to 1 that determines the degree of influence states. Here, how the GRU processes information. Gate computational. This is the first step. Calculate the update and reset gates using the current input and the previous hidden state with sigma acquisition. Filter past information. Apply the reset gate to previous hidden state, creating a filter version that emphasizes the relevant past data. Calculating the candidate. Compute candidate hidden state using the filtered information and current input with the TAN activation. And the last one is the update state. Combines previous and the candidate states using the update gate, creating the new hidden states for next time step. Here we have to compare between the GRU and the LSTM. The first difference is architectural similarity. Here, GRU gates update and resets unified and hidden state. Here, the LSTM has a three gates: input, forget, and update. Training speed. Uh, GRU faster training due to the fewer parameters on the operations. LSTM slower training with more complex computation. Computation cost. Next factor is the computational fact. GRU lower memory and LSTM uses the higher resource demand with more parameters. The precision control. Most good performance with a similar control. And the LSTM is more fine grained control over memory. Thank you. Thanks for giving this opportunity.